Hello friends, welcome to my channel. In this video I will cover previous year GATE papers Thermodynamics and Heat Transfer 2017 second shift I will cover. This is part 2. Heat exchanger question. In a counterflow heat exchanger, water is heated at the rate of 1.5 kg per second from 40 degrees Celsius to 80 degrees Celsius by an oil entering at 120 degrees Celsius and leaving at 60 degrees Celsius. The specific heats of water and oil are 4.2 kJ per kg Kelvin and 2 kJ per kg Kelvin respectively. The overall heat transfer coefficient is 400 watt per meter square Kelvin. The required heat transfer surface area in meter square is how much? So data given are counterflow heat exchanger, cold fluid is water, hot fluid is oil, inlet and outlet. So counterflow heat exchanger, hot fluid here, hot fluid or oil, cold fluid or water. Hot fluid inlet temperature is 120 degrees Celsius to 60 degrees Celsius. Outlet temperature THI is 120 degrees Celsius. TH at exist is 60 degrees Celsius. Like this, cold fluid or water inlet temperature it's 40 degrees Celsius. At exist, cold fluid temperature is 80 degrees Celsius. Delta Ti at inlet, it's the temperature difference between THI and TCE. Here, delta T at exist, it's the temperature difference between THE and TCI. So, here cold fluid mass flow rate is 1.5 kg per second. Then Cp also given. Cp of cold fluid is 4.2 kJ per kg Kelvin. Hot fluid Cph 2 kJ per kg Kelvin. Overall heat transfer coefficient U, it's 400 watt per meter square Kelvin. So calculate delta Ti. Delta Ti is THI minus TCE, this difference. Hot fluid inlet temperature minus cold fluid exit temperature. So 120 minus 80, it's 40. Like this, delta T at exist, it's the difference between THE minus TCI. Hot fluid exit temperature, it's 60 minus cold fluid inlet temperature 40, its value is 20. So calculate delta Tm, log mean temperature, it's Tm delta Ti minus delta Te ln delta Ti divided by delta Te. So delta Ti we got 40 minus 20 divided by ln 40 by 20. In some examination they won't allow calculator and they will ask this type of question. So ln2 value you have to remember 0.69, that value you have to remember. In GATE no problem, they will allow calculator, virtual calculator they will give, but for other examination you have to remember ln2 value. So 28.98 it's coming, delta Tm, then Q heat transfer mCp dt, m dot for cold fluid given, so cold fluid you apply here m dot c into Cpc to cold fluid exit temperature minus cold fluid inlet temperature. Put the values. M dot mass flow rate is 1.5 into Cp is 4.2, it's kilojoule. 80 minus 40, so we'll get 254 kilojoule per second. U value also given, overall heat transfer coefficient. So heat transfer Q is UA delta Tm. Here you can write delta Tm or simply Tm also, log mean temperature value. So from here you will get A value. A is Q by U into delta Tm. You will get 254, it's in kilojoule, so 10 multiply 10 to the power 3 divided by U value given, overall heat transfer coefficient 400 into delta Tm we already get 28.98. So if we solve this one, we will get 21.9 meter square. So from option D is the answer. This is 2 mark question. Options also available, so careful. Negative marking is 0.66 mark. So careful while solving this question. This is also 2 mark question, but option is not available, so negative marking is not there. In the Rankine cycle for a steam power plant, the turbine entry and exit enthalpies are 2803 kilojoule per kg and 1800 kilojoule per kg respectively. The enthalpies of water at pump entry and exit are 121 kilojoule per kg and 124 kilojoule per kg respectively. The specific steam consumption in kg per kilowatt hour of the cycle is we have to find. Okay. Rankine cycle. This is the basic diagram for Rankine cycle. Boiler, then turbine, then condenser, then pump. Pump is series centrifugal pump. Boiler, from pump it's 1 to 2, 2 to 3. In boiler 3 to 4 expansion. In turbine 4 to 1 heat is going out. So in TS diagram, this is 1 to 2 pump, 2 to 3 boiler, 3 to 4 isentropic expansion, then 4 to 1 condensation. So in this question given are turbine entry and exit enthalpies are given. Turbine entry or H3 2803 kilojoule per kg, H4 it's 1800 kilojoule per kg, pump entry, it's 1 H1 121 kilojoule per kg, H2 it's 124 kilojoule per kg. Specific steam consumption we have to calculate. Specific steam consumption or steam rate 1 by W net. Its formula is 1 by W net. Unit is kg per kilowatt second. But in this question they asked for kilowatt hour. So 3600 divided by W net kg per kilowatt hour. So W net we have to calculate. Net work done. Net work done is here work out and work in. This difference is net work done. So W turbine minus work done in pump WP. W turbine is H3 minus H4 minus W pump is H2 minus H1. So put the values. H3 minus H4 it's 2803 minus 1800 minus it will come 124 minus 121. You will get 1000 kilojoule per kg. So put the value, you will get your answer. Steam rate or specific steam consumption rate. Steam rate 3600 divided by W net. Net work done. So 3600 divided by 1000, you will get 3.6 kg per kilowatt hour. Sometimes they may ask in kilowatt per kg per kilowatt second. That time that unit you have to check in which unit they ask the question. So whether you have to multiply this one or not, you have to decide according to that unit. So here they ask kilowatt hour, so 3.6 is the answer. So numerical value is 3.6, unit is kg per kilowatt hours. Just you have to enter the numerical value 3.6. This is also 2 mark question. Here no negative marking. Question is 1 kg of an ideal gas constant given R equal to 287 joule per kg Kelvin undergoes an irreversible process from state 1. State 1 conditions are pressure 1 bar, temperature is 300 Kelvin to state 2 bar and 300 Kelvin. The change in specific entropy S2 minus S1 of the gas in unit is joule per kg Kelvin in the process is how much? So we know for entropy change 3 formulas are there. Cp ln V2 by V1 plus Cv into ln P2 by P1 Cv ln T2 by T1 plus R ln V2 by V1. Third formula is Cp ln T2 by T1 minus R ln P2 by P1. According to your data, you have to choose which formula you have to use. So here data given are mass is 1 kg, R is 287 joule per kg Kelvin, irreversible process. P1 given 1 bar, T1 300 Kelvin, state 2 pressure is 2 bar, P2 temperature is T2 300 Kelvin. So here pressure and temperature given, so you have to choose pressure and temperature. Here third one you will get pressure and temperature. First and second you don't have to use in this question. So T1 equal to T2, this value is 0, S2 minus S1 is minus R ln P2 by P1. R value is 287 into ln P2 by P1, you will get ln 2.69, 287 into 0.69. This type of question in ISRO also they are asking this type of question. That time you won't get calculator, so you have to remember the ln value. So you will get minus 198.93 joule per kg Kelvin. So you just have to enter the numerical values, minus 198.93. 2 mark question. Option is available, so negative marking is there, 0.66 negative marking. So while solving you have to careful. The volume and temperature of air assumed to be an ideal gas in a closed vessel is 2.87 meter cube and 300 Kelvin respectively. The gauge pressure indicated by a manometer fitted to the wall of the vessel is 0.5 bar. If the gas constant of air is R equal to 287 joule per kg Kelvin and the atmospheric pressure is 1 bar, the mass of air in kg in the vessel is how much? This is a ideal gas. Volume is 2.87 meter cube, temperature T is 300 Kelvin, gauge pressure is 0.5 bar and atmospheric pressure R value given 287 joule per kg Kelvin. Atmospheric pressure P atm is 1 bar. So from here absolute pressure we can get P absolute pressure is P atm plus P gauge. P atm P gauge total is P absolute. 1 plus 0.5, 1.5 bar or 1.5 into 10 to power 5 Newton per meter square. Then put ideal gas equation, PV equal to MRT. So mass we have to find PV divided by RT, 1.5 into 10 to the power 5. Volume is given 2.87, R is 287, 300. So get 100. So 15 by 3, 5. M dot, this is only M, 5 kg, M equal to 5 kg. So from option you have to check. See the answer. Thank you friends. Thank you for watching my video. Thank you.